Hi there. I'm going to cover some energy fundamentals that students need to know for Physics C. I'm going to cover topics such as defining the conservation of energy, how to graphically solve a problem, working through example energy problems that involve a hanging mass or a spring. So let's get started. The relevant equations for energy are delta energy is equal to work, which is equal to the integral of force times the differential distance. You can rewrite this as F is equal to the derivative of work with respect to R. K, or kinetic energy, is equal to 1/2 mv squared. Power is equal to the derivative of energy with respect to time, which is also equal to force times velocity. Our delta potential energy is equal to mg delta H. And then we also have force is equal to the negative derivative of potential energy with respect to distance. And we talked about this very briefly a couple units ago, and we'll talk about it again. Another really important equation that I would have memorized is that U initial plus K initial is equal to potential energy final plus kinetic energy final. This can also be re-represented as delta U is equal to negative delta K. Or if signs are really tricky for you, I would probably stick to this convention that delta U is equal to the absolute value of delta K. So let's do an example problem in which we use all three of these equations to show that they're all the same. So let's say that you have a ball and you drop it and it hits the ground. And let's say that this was at a height of 80 meters. And this mass is 2 kilograms. What is the speed of the ball by the time that it hits the ground? So let's start with this equation. U initial is equal to mgh initial. So that's going to equal to 2 times 10 and a height of 80. So that's going to give you 1600 joules. Kinetic energy initial is equal to 1/2 mv squared, which is equal to 1/2 times 2 times velocity, which was initially 0 since it's being dropped. That's going to give you 0 joules. Let's look at the final potential energy. So mgh final is equal to 2 times 10 times 0 because the height is now at its lowest point. That's going to give you 0 joules. K final is equal to 1/2 mv squared, which would give us 1/2 2 v squared, which we do not know yet, but when we compute this, it should be v squared joules. All right, so let's look back at our equation. U initial plus kinetic energy initial is equal to U final plus K final. And we both determined that the initial kinetic energy is equal to 0 and the final potential energy is equal to 0. So we have U initial, which is 1600 joules, equal to our kinetic energy final, V squared joules. So V is equal to square root of 1600, which will give us 40 meters per second. All right, now let's use this equation. Delta U which is equal to mg delta H is equal to 2 times 10 times, so we went from a final height of 0 and our initial height was 80. So that gives us negative 1600 joules. So our delta K is equal to negative delta U, which is equal to 1600, which is equal to 1/2 2 times V squared. And to equate these, we will get V squared is equal to 1600. And to solve for this, we will get V is equal to 40 meters per second. Just the same answer as we got here. And very lastly, using this equation, delta U is equal to the absolute value of delta K. So when we calculate delta U, we got negative 1600 joules. The absolute value of 1600 joules is equal to 1600. Therefore, when we solve for velocity, we will still get 40 meters per second. So again, this is helpful if you have a hard time picking which is your 0 point. However, I will always define them in our future problems in this video. The one really important thing about this equation, delta U is equal to delta K, is that we can derive this equation. If delta U is equal to negative delta K, then U is equal to negative F times the differential distance, because we have work is equal to F times the differential distance, and work is the same thing as kinetic energy. So taking the derivative with respect to each side will give us negative F dr, and therefore we gather that F is equal to negative du with respect to r. Let's do an example problem where we have force along the y-axis and distance along the x. A common question that you may be asked is, how much work or kinetic energy was done on the system, right? So we know from our equation that work is the integral F times the differential distance, which means we need to take the area underneath the curve. So work is equal to FDR, which is equal to, so let's do the area of this triangle, 1/2 base, which is 3, height of 4, plus the area of this square, which is 7 minus 3, which is 4, and a height of 4, plus then the area of this triangle, 1/2, 8 minus 7, which is 1, and the height of 4. So this will give us 6 joules plus 16 joules plus 2 joules, just give us 24 joules. Another question that they might ask is, what is the delta U of the system? In this case, we have delta U is equal to negative delta K, which will equal to negative 24 joules. Hence why you also need to have these two equations memorized, even if you do like to use this more often. Next question, if this was done over 4 seconds, what is the average power dissipated by the system? And this is a key word, average. So we know that power is equal to the differential energy with respect to time. We can rewrite this because of this average keyword, energy with respect to delta time. So we have an energy of 24 joules all over 4 seconds, which is equal to 6 joules per second. So this is going to segue the next topic I want to cover, which is simplifying differentials. So we have our equation, change of energy is equal to the integral of F times dr, which can be simplified to F times delta R, only if F is constant throughout delta R, P is equal to the differential power is equal to the derivative of energy with respect to time, which is also equal to E over delta T. This only works if energy is constant throughout delta T. Let's look at this equation first. Only if F is constant throughout delta distance. So between 3 and 7, we have a constant force, hence why we were able to just multiply our force with our delta distance, which is 7 minus 3. Now let's look at this. We asked for the average power dissipated by the system. However, by looking at this, I can't just determine if energy is constant throughout time, but this is asking for average power, and hence we can consider that as an exception to this rule. If you see the word average, the first thing that should come to mind is simplifying your differentials to look like this. And this goes for any other equations that we simplify in the previous units. Let's do another example. So let's look at this problem. How much work is done by Joe if Joe lifts a 2-kilogram box 6 meters up at an acceleration of 1 meters per second? Now this is getting really tricky because most students will just put F is equal to ma, which is equal to 2 times 1, which is equal to 2 newtons, and then work is equal to just F times delta R, which will then be 2 times 6, which is 12 newton meters. However, this is wrong. This is not the correct calculation of force that's being applied. You are forgetting the force of gravity. So let's draw our free body diagram. F of G, and then F of, let's say, Joe. So our acceleration is equal to sum of all the forces divided by mass. So all the forces would be the force applied by Joe minus the force of gravity all over its mass. So to solve for the force that Joe applies, you need to rewrite this as AM minus FG So let's plug in our values. We have an acceleration of 1, and it's going up, and a mass of 2 minus our f of g, which is gravity, which is going down, so we're going to assign this a negative value, times its mass, which is also 2. So this reduces down to 22 newtons, which is very different from the 2 newtons that most people will calculate. Okay, then your work is equal to F times delta R, which is equal to 22 times 6, which is equal to 132 newtons. This is a very common problem to have, especially in the multiple choice, is for getting this F of G. Now let's look at a problem when Joe is not applying a force straight up. Let's say that we have the same block. However, now it's going to be on a plane. So it's moving across the ground. And Joe applies a force at an angle. All right, and we won't neglect force of friction. So let's say the block is moving to the right. So let's draw our FBD. We have our force of gravity. So let's see, we have our force of gravity. We have our force of friction, again in the opposite direction of our velocity. And now that we have this surface, we also have this F of n value. So a question that might be asked is, how fast is the block moving? What is the acceleration or the net acceleration of the block? So, as always, when you see a diagonal, first thought should be to split your F into X and Y components. So, if we look at Joe, force applied by Joe, we have its X component, which is located here, and its Y component, which is along this dotted line. So let's sum of all the forces in the Y direction. So we have F of n, which is positive, so we're going to keep the positive, minus F of g because of the force is applied downwards. And then we also have the force that Joe applies in the Y direction. Because this is going upward, that's going to be positive. Now, as we can tell from this block is not levitating. Again, we are saying this block is sliding along this surface only. So this means that all the forces, all the sum of the forces has to equal to 0. Hence, the acceleration in the Y direction is equal to 0. So our normal force is equal to F of G minus F Joe in the Y direction. Now let's look at the sum of the forces in the X direction. So we have F of Joe in the X, and we're going to keep this positive because the vector is pointed to the right, and then minus force of friction because this vector is pointed to the left. We can say that this is equal to ma because we know that this is pulled at some sort of velocity, so we have some sort of acceleration. Now, what is the force of friction? Which is equal to mu, some constant given to you by the surface, so mu F of n. Well, F of n is going to equal to this. So all the forces applied in the X direction is equal to f of Joe x minus mu fg minus fjo in the y direction, which is equal to ma. And because we have theta, let's replace this x and y components with the values that were given. So it would probably be f of Joe. In the x direction, cosine theta minus mu fg minus fjo sine of theta. So to solve for acceleration, we'll get fjo cosine theta minus mu fg fjo sine of theta all over its mass. And one thing I forgot to put on here is acceleration in the x direction. However, since the acceleration in the y direction is equal to 0, this will also equal to the net acceleration of the block, because Pythagorean's theorem is as such. If this goes to 0, that means A is equal to acceleration in the x direction. Now let's look at the calculation of work done by Joe. So now let's look at the work that's done by Joe. So work is equal to F delta R. And let's say that this block is moved 6 meters instead of up to the right in this scenario. So that means let's look at the forces in the y direction first. So we know that this block is not levitating or moving up and down because the acceleration in the y direction is equal to 0. So that means that the work done in the y direction is also equal to 0. Let's look at the work done in the x direction. So force applied in the x direction is going to be this entire thing. It's just times delta R, which would equal to 6 meters. Even though this is the energy unit, you can see how the forces and FBDs are still very, very important when it comes to answering energy problems. So the work done by Joe is equal to the work done in the x direction. Again, because work done in the y direction is equal to 0. Now let's look at the different types of problems that you will see on the multiple choice and or free response. You usually have either a hanging mass, mass with a spring, or some sort of rotational inertia problem. And we're not going to dive into this in this unit. We're going to do it in the next one because we won't really talk about rotational inertia quite yet. All right, so let's look at the hanging mass. So let me just copy and paste this. And let's define some of these variables. Let's say that the length is equal to 4 meters and the mass is equal to 2 kilograms. This theta is equal to 60 degrees. And let's say that this block is dropped so that its final destination appears here, or at least passes through this point. So a common question that might be asked is, what is the velocity of the block at point 2, signified here? So the first step you want to do is find the initial height of the block. So let me redraw this portion of the diagram. So the height of the block, let's name this portion 0 meter mark. So the height of the block is going to be its y component of this string. So because it's adjacent for cosine of 60 degrees. So that's going to yield 2 meters. So this block is going to be 2 meters, I guess negative, because if we're assigning this as 0, going down is negative, 2 meters from where the string originates from. 2, find the change in height. So we'll have delta H is equal to height final minus height initial. So our initial height was negative 2. And if this block goes all the way down, this string will also follow. So that means its final height, this point, I know it's not very drawn to scale, it's going to be the length of the string, which is going to be negative 4 in this case. So negative 4 meters minus negative 2 meters, that gives us a change of negative 2 meters. So the block drops a height from minus 2 meters to minus 4 meters. Next, we're going to find delta U and delta K of your block. So delta U is equal to mg delta H, which is equal to 2 times 10 times negative 2, which will give you negative 40 joules. So that means your delta K is equal to 40 joules. Again, if signs are very strange for you, let's say that even this portion was difficult to understand, delta U is just the absolute value of delta K. If you understand that one of these values is supposed to be negative, which is usually, if not always, the potential energy, just make sure that if you write instead positive 2 meters and put 2 here, that your kinetic energy is not going to be negative 40, but still positive 40. But this is a conceptual check. Okay, now let's find the velocity. So K is equal to 1/2 mv squared. So V is equal to square root 2K over m. So we have square root of 2 times 40 joules all over 2, which equals the square root of 40. So that means our velocity is equal to 6.32 meters per second. So by the time that this ball drops to its minimum point, its velocity is equal to 6.32 meters per second. Now let's look at mass with a spring. Let's copy this down over here. let's say that the initial velocity of the ball is equal to 0. This is a 2 kilogram mass ball. This is at a 20-meter height, and the force of friction is equal to 0. A common question is, what is the speed of the ball at the bottom of the ramp before it even hits the spring? So let's just use this equation. Delta U is equal to negative delta K. And I like to write it this way because you can see that mass cancels out always. So, and we could do that in the previous problem as well. However, if the problem doesn't give you mass, you probably don't need it, and it usually gets canceled out when you equate these to one another. So let's solve for V, which is equal to square root negative 2g of 8, which is equal to negative 2 times gravity times height, which drops by negative 20. So this will give us 20 meters per second. By how much is the spring compressed if K is equal to 10? So that means by the time that the ball reaches to this point, we want to know what this delta x is. Let's write this equation first. So at this point, when the ball rolls all the way down the ramp, right before it hits the spring, that's the initial point. And the final point is when the ball compresses the spring. So the U initial, because it goes all the way down to 0, is also equal to 0. And we have only kinetic energy, which we have here, with a velocity of 20 meters per second. Now, when the ball compresses the spring fully, the ball is completely stopped. So that means that its velocity is equal to 0. So the final kinetic energy is also equal to 0. And all the potential energy, this U final, is going to be in the spring. So its kinetic energy initial is equal to 1/2 mv squared, which is equal to 1/2 times 2 times 20 squared, which is equal to 400 joules. Now this is going to equal to your potential energy in your spring. So that means that you should use your equation. U of S is equal to 1/2 K delta X squared. Rewriting it to solve for delta X, we have square root of 2 delta U of S all over K, which will give us 2 times 400 joules all over 10, which means that the spring is compressed by 8.94 meters. Now, if you have any questions or concerns, please let me know. If you see any errors in the videos, please comment below. And thank you for watching.